Hello. So I'm going to run through the teaching of thermodynamics. There's no class in front of me today. It's just me in the lab. It's the end of the year. I've got a bit of game time, so I thought I'd spin out a few of these. Thermodynamics, which just means heat change, right? It's the study, it's mainly physics, the study of how heat changes in systems. And if you want to look up the laws of thermodynamics, feel free. They're mostly useful to physicists. For chemists, I just wanted to go back to the topic that we generally do in about November, December of year 12, which is the first energetics topic. And we introduced the topic of the concept of delta H, enthalpy change, or chemical heat energy change, and Hess's law. So Hess's law, enthalpy change for a process is independent of the route taken, and our definition of delta H, which is enthalpy change at constant pressure, and then we have the little London Underground sign, the little standard sign, which means it's done at 298 Kelvin and 100 kPa. And then we introduced a couple of sort of special delta H's. So we had delta HF and the enthalpy of, I can't spell, standard, if we put a standard on it, the standard enthalpy of formation I'm going to put the standard enthalpies over here actually. Delta HF, standard enthalpy of formation. You can look it up if you like, but remember it's the enthalpy change to make 1 mole of substance from the elements, all substances in their standard states. That's our delta HF. There's going to be quite a few definitions in the early part of this topic, so you might want to have the booklet open. I'm obviously just starting the topic, so we're right at the beginning of that. So you might remember we used standard enthalpy of formation data to work out delta H for reactions. So if I had a simple reaction of sodium hydroxide and hydrochloric acid, so then I could think about, okay, what are all the elements here? I've got sodium, and I've got half an O2 molecule, I've got half an H2 molecule, I've got half a Cl2 molecule. So those are my elements down there, and those elements go to make all of the different compounds there. And if I have the delta HFs of these and the delta HFs of those, then overall the delta H is the sum of, sorry, writing's rubbish, but it's hard writing down here, trust me, of the products, take away the sum of the delta HFs of the reactants. And the reason for that is that if I'm going from reactants to products, then I'm going in the opposite direction to those arrows, so I have to change the sign for those delta H's. So that was another rule we introduced. If you go with the arrow, you keep the delta H as it is, go with the arrow. If you go against the arrow, you change the sign of the delta H, because if a reaction's 50 kilojoules going forwards, it's minus 50 kilojoules going backwards. So that's our Hess diagram, or a Hess cycle, which helps us work out the value of a delta H using Hess's law. So that's all stuff that we introduced in the energetics topic. What we're going to do now is take that and some more special delta H's we did introduce the mean bond enthalpy, didn't we? Mean bond enthalpy is the mean bond enthalpy. The enthalpy change when we take 1 mole of bonds and break them, averaged over different compounds, but in this case that I've done, you can't have different compounds of Cl2, can you? So it wouldn't be averaged in this case, but the energy required to break 1 mole of chlorine bonds to make 2 moles of chlorine atoms, all in the gas phase, would be its bond enthalpy, the bond enthalpy of the chlorine bond. So that's another one that we met as well. We also met enthalpy of combustion, but we won't be revisiting that in this topic. Okay, so I'm going to leave that side of the board free there, and I'm going to draw a big Hess diagram on this side. It's called the Born Haber cycle. The thing that makes a Hess diagram or a Hess cycle different from a Born Haber cycle is a Born Haber cycle doesn't just have arrows for the different reactions. It keeps an axis on the left here going upwards for energy. Okay, in exactly the same way when you draw the reaction profile diagrams, you have a sort of an energy axis there, and therefore you can see that an exothermic reaction goes down because things are losing energy, and an endothermic reaction goes up. So it's going to be the same for this. Let me just write that on. So if I'm going upwards, that's an endothermic reaction. If I'm going downwards, that'll be an exothermic direction. Okay, exo losing energy to the surroundings, endo gaining energy from the surroundings. Okay, so this is going to be a Born Haber cycle for sodium chloride, is what we're interested in. And I'm going to put sodium chloride right at the bottom. That's where it goes. Solid sodium chloride will be right down there. Okay. Well, we know one delta H already. We know the standard enthalpy of formation, which is the enthalpy change when 1 mole of substance is formed from the elements, everything in its standard state. So what's sodium chloride formed? Well, it's formed from sodium, which is a solid at room temperature, and chlorine, which is a gas at room temperature. Now, I only need 1 chlorine, but chlorine comes in pairs, diatomic molecules, Cl2. So I have to say half a Cl2 there. Okay. Now, there's another way of making sodium chloride that I'm interested in, and we'll see how it becomes useful later, and that is the lattice formation. Lattice formation enthalpy, which is the enthalpy change to make 1 mole of solid salt, but from gaseous ions. Okay, so that means up here I must have gaseous ions. Okay, so the Born Haber cycle attempts to stitch these two together. So in other words, I'm going to try and get all the way around here by having connecting ideas so that my sodium and chlorine elements in their standard states can get to sodium and chloride ions in the gaseous state. And the way I'm going to do that is break it down into a series of steps. So if I think about sodium solid, I need to get it to sodium gas. So the first step will be turning sodium solid into sodium gas. Now, you might go, okay, first I have to melt it and then I have to boil it. But there's a quicker route which we can take, which is the enthalpy of atomization. Enthalpy of atomization makes 1 mole of gaseous atoms from anything. So if I start off with sodium solid, I would make 1 mole of gaseous atoms. Remember, it's atomization, not ionization. We'll come back to ionization in a moment. So we're going from sodium solid to sodium gas there. So this first step is the atomization of sodium. Okay. So all I've changed is the sodium. I haven't changed the chlorine, so that's still half a Cl2 gas. But let's do the chlorine now. So if I was to atomize chlorine, then I'd have sodium vapor, sodium atoms, and I've now got 1 mole of chlorine atoms there. So enthalpy of atomization, remember, produces 1 mole of atoms. So half a Cl2 gas goes to 1 mole of Cl gas. Now just notice the difference here between this one and this one. They both do the same thing. They both turn Cl2 into atoms, Cl2 molecules into Cl atoms, but the definition of atomization is to make 1 mole of atoms, whereas the definition of bond enthalpy is to make 1 mole, is to break 1 mole of chlorine-chlorine bonds. So if I'm using bond enthalpy data, I'll make 2 chlorine atoms. If I'm using atomization data, I'll make 1 mole of chlorine atoms. This is just one of the ways in which questions on Born Haber cycles are going to trip you up. Do I need to multiply that by 2? Do I need to divide that by 2? It's going to become important. In this case, if I've used atomization data, that makes 1 mole of chlorine atoms. I only need 1 mole of chlorine atoms because I'm making NaCl. So 1 is fine. So no multiplying or dividing of anything. Okay, where do we go next? Well, we need to turn our sodium atoms into sodium ions. Okay, so if I take sodium gas and turn it into sodium plus ions, plus an electron, don't forget the electron, that has to be on the Born Haber cycle as well. Well, we know what that is. I'm just going to say ionize, i.e. that's the ionization energy or ionization enthalpy, or enthalpy of ionization. Or if you want to be really strict, the first ionization enthalpy, because it would be possible to pull off subsequent electrons from sodium. Okay, we're nearly there. We just have to take that spare electron that we just pulled off chlorine and give it to the chlorine. Sorry, take the electron that we pulled off sodium and give it to chlorine, and that will make this delta H here. It's called the enthalpy of electron affinity. The enthalpy of electron affinity, that's where I take an atom, give it an electron, and turn it into a negatively charged ion, all in the gas phase. It's kind of the opposite of ionization enthalpy. Ionization is always about taking an electron from an atom electron affinity is always about giving an electron to an atom. Okay, so of all of these changes, you might have noticed I've gone down here, of all of these changes, that is the only one which is exothermic. The reason for that is that if I give an electron to chlorine, I'm making I'm satisfying that force of attraction between the electron and a positive nucleus. As that electron falls into the atom, gains its place on the outer shell, energy is released. In exactly the opposite way to pulling an electron out of an atom, if I pull an electron out of a sodium atom, I have to do work in order to get that electron away from the charge of the nucleus, so that requires me to put energy in. So ionization, first ionization is always endothermic, first electron affinity is always exothermic. Okay, we have finished. We've got all the way around. And now what we can do is we can put numbers in. We look these up in data booklets or in exam questions. They'll be given to you in a data table. So enthalpy of formation, I haven't put that in, have I? Enthalpy of formation of sodium chloride is also exothermic because sodium chloride is a pretty stable compound. Minus 411. The atomization of sodium, plus 107. The atomization of chlorine, plus 121. The first ionization energy of sodium, plus 502. And the electron affinity of chlorine, minus 355. Which means the only bit that's missing is the lattice formation enthalpy. Let me put this up here. Okay, so standard Hess cycle rules apply. If I go from here to here, the energy change for that process is independent of the route taken. So the enthalpy change going from here to here, the lattice formation enthalpy, is going to be the same as going all the way around. So from here to here, that would be plus 355, and then going from here to here would be minus 502. Notice I'm going in the opposite direction to the arrows, which is why I'm changing the signs down here. Minus 107. Down here I'm going in the same direction as the arrows. Minus 411, which is minus 786 units, of course, as always, kilojoules per mole. So in essence, with a Born Haber cycle, we're doing the same job as we did with a Hess cycle. It's just there's quite a lot more legwork to get there. Okay, let me run through another example. I just want to find one with a 2 in it. Let's do a Born Haber cycle. Hello. For, what do we got here? Magnesium chloride. So again, we start off at the bottom with the salt in its standard solid state. And the first arrow we put in is the enthalpy of formation, standard enthalpy of formation of that compound. And standard enthalpy of formation is always from the elements in their standard states. Now I have to get all the way around, so we could start off by atomizing magnesium. So that would produce 1 mole, sorry, no plus charge, 1 mole of gaseous atoms. We could then do the same for chlorine. But because I'm making 2 moles of chlorine atoms for MgCl₂, I'm going to need 2 lots of the delta H atomization of chlorine. Now we need to ionize. Let's just do that in 2 steps. So we've got the first ionization energy, and we're going to call that IE1 of magnesium to make Mg+. Don't forget the electron. And then just about squeeze it in here. Maybe I'll rub out the title, give myself a bit more headroom. The second ionization enthalpy of magnesium would give me Mg2+ gas state, 2 electrons and 2 chlorine gas. Now we can come down again with 2 lots of the first electron affinity for chlorine. That would take my 2 electrons, give them to the chlorine. So I've now got Mg2+ gas, sorry, 2 chloride ions, gas phase, and that means we are ready now to go for the lattice formation enthalpy of MgCl₂. Just beware, there is another enthalpy that you'll find in the books, and that's the lattice dissociation enthalpy. The lattice dissociation enthalpy is the enthalpy change when we take 1 mole of compound in its standard state and break it into gaseous ions. Now, of course, that's the exact opposite definition of delta H lattice formation. So lattice formation that was supposed to be a standard symbol. It's difficult to write down the bottom of the board. Lattice formation enthalpy is whatever the lattice dissociation enthalpy was, just with a negative sign. Really struggling there, aren't we? Okay, so just be aware, lattice formation is always going to be a very big negative number. Lattice dissociation is always going to be a very big positive number. It's the same number, just a different sign, but that's just another way that they can throw you. Okay, so common mistakes that people make in Born Haber cycles. Well, number 1 on my list would be forgetting the electrons. Because often the question will be in the exam, just they'll leave some of these blank and they'll ask you just to fill in the species on each of those different lines, and quite often the electrons are forgotten. Don't forget the state symbols as well, but you guys are getting much better at state symbols by now. You've done a year of year 12 chemistry, but the electrons can often get forgotten. The second thing that gets forgotten is the number 2. So for magnesium chloride, because I'm making 2 chlorines, I'd need 2 enthalpies of atomization, 2 electron affinities. Sometimes I see the number 2 where it's not needed. So for example, if they gave the in the data for this one, if they gave the bond enthalpy of Cl2 Remember, bond enthalpy for Cl2, I'm running out of board space. The mean bond enthalpy for Cl2 would be Cl2 reacting to make 2 chlorine gaseous atoms. So if they gave you the bond enthalpy, you wouldn't need the number 2 here. You would just have one lot of the mean bond enthalpy, for Cl2, because bond enthalpy is changing one Cl2 molecule into 2 Cl atoms, everything in a gas state by definition. So we've satisfied that. So I'll see people multiplying things by 2 when they don't need it. Similarly, if you were given the bond enthalpy for sodium chloride over here, then we would need a half of the bond enthalpy for Cl2, because we're turning half a Cl2 into a chlorine atom, so that's half as much energy as would be required for turning 1 mole of chlorine molecules into 2 chlorine atoms. Okay. All right. That's my little introduction to Born Haber cycles. I hope that was helpful. Get lots of practice. There's plenty in the topic booklet. Make sure you can do them quickly and easily. You could get a question in the exam where they just give you a blank piece of paper and say, draw the Born Haber cycle for magnesium chloride. And then they give you some data and you put in the numbers and off you go. So be ready for that.